So, Go Nuts and Bolt. Go Nuts is the mailing list, and Bolt is this awesome database library, key value store library. It's on GitHub. There's an interesting delay before the slide switches. If that doesn't update, tell me. It updates on my screen. Okay, so Bolt is on GitHub as BoltDB/Bolt. It's a project primarily by Ben Johnson, who's an awesome dude. He writes really neat code. If you're looking to understand something that's a little fiddly with like low-level details, but really written, that source code is really a good experience to go through. My involvement with Bolt has been mostly to be a sounding board for API designs, and I submitted a couple of features. I'm a heavy user, and I'm here as a user telling you that Bolt is awesome. Does that actually work?
If you want to hold it.
Yeah. Can you hear me okay?
Yeah.
Okay. I'd rather have my hands free. So Bolt is a key value store. It's not a full database. It's not a SQL database. Definitely not. It's a key value store. This key has this value. And basically, you open a file. You do put operations where this key is this value. You do get operations where you give in the key. And all of these are byte slices. So there is no like numerical data types, none of that stuff. That belongs in your application or a wrapper you build on top of Bolt that actually understands your data types. As far as Bolt is concerned, everything is a byte slice. And we'll talk more about buckets later. So Bolt is pure Go, and that's one of the reasons why it's so amazing, like why I enjoy using it. It was inspired by a project called LMDB, which was written for OpenLDAP to serve as the backend for that product. And it has the same basic design, but it is not a Go port of LMDB. It has different design goals, and they are starting to deviate from each other. Bolt is explicitly as simple as it possibly can be. Even if that costs a little bit of performance, Bolt chooses to be simple and understandable. LMDB is for performance nuts, written in C or C++, I forget which one, and explicitly meant for that sort of stuff. Bolt is simple, pure Go, and a joy to use. Bolt is a library. It's not a network service. It's not something that runs independently of your application. It is a part of your application. And it is literally a file format that you use through this library. So it's a single file, which makes it really easy to manage. You could write network bits on top of it, but it's probably better to provide like more value instead of just getting input operations. And InfluxDB, which is the second talk of today, is kind of an example of using Bolt in your own application. Bolt databases are meant to be used by a single process. So there is a single owner of the database, one at a time. So if somebody has the database open, nobody else can open it at the same time. And the key value store is ordered. So you can walk the keys in order. So here's an example of, first thing you have to remember is that the keys and the values are just byte slices. So to be able to have a meaningful order, we need to encode our values in a way that preserves the order. So here, we're doing zero padded decimals. Nice delay on the mouse. Right there. We're doing zero padded decimal strings as the key. In your real application, you'd probably do something a little bit more binary, but the same idea is there. So for example, big endian is order preserving for integers, unsigned integers. So we go through and put in 100 random keys from 0 to 9999, and then we walk through them in a for loop. And what you get out is you get a listing of, there we go. I'll see. So then we get them in order. There's an interesting delay going on with the airplay there, but I better not scroll things. Okay. So an ordered key value store also lets you access data by other like gimmicks. Like you can ask for anything with this prefix. So we stored 4-digit decimal numbers And we can ask for anything that begins with a 4 and a 0. In our 100 random numbers, there are 2 of those. You can ask for a range by encoding both the beginning and the ending key the way you encode keys, and walking a cursor from the beginning key to the ending key, as long as you don't go past the maximum key. So it's kind of fairly simple, but you can see how this is not like writing a SQL query. You're actually like programming it with a fairly low-level mechanism. This actually feels like I'm using an in-memory data structure, like a container of some sort would have this API. Now it just is a persistent data structure. So Bolt actually is a B+ tree underneath. That's what's stored in the file. And because saying B+ tree is annoying, and technically B trees are something slightly different, I'm going to say B tree, and it's going to be a B snowman tree. Okay, so it's a copy on write B tree that begins with 2 metadata pages. Which one is newer is the one that wins. So when we're opening the database, recovering from a crash or whatever, which one of those 2 metadata pages has a higher stamp generation counter on it, that one wins. And that page contains pointers to the rest of the stuff. The rest of the stuff is data pages that contain the buckets that we talked about, that have the keys in them, they have the values, and then there's a list of which pages are free that is also stored on the pages themselves, which is a neat trick. Think about that for a moment. It keeps track of what's free in its own free space. That sounds like malware. This sounds like an in-memory data structure. Huh. There's a reason for that. Anyway, when you do a transaction and an update transaction, a write transaction, first it writes out all the dirty data pages to new locations. So that's a copy on write operation. And then it writes over the redundant metadata page, which now becomes the new one. So every single write transaction that you do is 2 disk flushes, 2 disk sinks. Read transactions pin the data that would otherwise be recycled and hold it from being recycled. But it's a big copy on write B tree that uses the file as its storage. So it has all the good and bad sides of B trees in general. And one of the sort of popular alternatives that gets mentioned is LSMs like LevelDB, for example. And these two are completely different in design, but used for similar purposes, which kind of leads you to the question of which one should you use. Well, the basic guideline is this. LevelDB was designed to take random writes and convert them into sequential writes as they go to disk. And the thing that benefits from that is spinning disks. So LevelDB is really intended for write-heavy operations running on spinning disks. It benefits from SSDs, but it really is designed for spinning disks. B trees tend to have a lot of random accesses, which, while they still hurt with SSDs, they hurt significantly less. So Bolt is really good when running on SSDs, and in general, the design is flipped all the way up, the other way around. So whereas a log-structured merge tree like LevelDB is write-heavy and reads are actually slower than writes, Bolt is the exact opposite. As heavy of a read load you can give, that's what it is built for. And writes are a little bit more expensive. The other thing is that log-structured merge trees tend to have these spikes of heavy I/O called compaction, where it cleans up the database. Whereas a B tree will do that on the fly all the time. So once again, it's a little bit slower on the average often, but it's steady performance, not spiky performance every now and then. Okay, we don't have much time to talk about that now, but find me later in this event and ask me questions. Because that's kind of off topic for itself. That's just a comparison against another thingy that is in a similar role. So, one of the reasons that makes Bolt pleasant to use is because it's simple. And one of the major ways it is simple is because it has a single writer at a time touching the database. So, if you think about your typical counter, for example. You read the counter, you increment the number, you store it back. Now somebody goes, you can't do that. You will have conflicts with two updates happening at the same time. Well, Bolt is explicitly designed so that that never happens. So doing the dumbest possible thing, writing the simplest possible code, is actually what is meant to happen with Bolt. You don't need to have this elaborate, for example, in SQL, you need to actually write a query that does the thing you want, instead of reading the value into your application, doing something for it, and putting it back in. So Bolt it feels more like programming than writing in some DSL, if that makes sense. And I actually prefer that. My data structures are fairly complex and there's a lot of intricate bits going on. So I like the guarantee that when function F is updating the database, no one else is. And this is called serializable as a property. And it's like one of the strongest things you could ever say about a database. And it costs some performance, but it makes things just so much easier to think about that I'm willing to do the trade-off personally. This is what a write transaction looks like. So you call the method dbUpdate, and you give it a function. You give it a function that takes a Bolt transaction and returns an error. And it may do things with the transaction to read and write the database. If it returns an error, it gets rolled back. If it returns success, the commit goes through unless there's a disk error or something like that. So you'll still, this is the actual error that tells you whether it went through or not. But essentially, if you say, oopsies, I take that back and return an error, Bolt undoes everything you did. And to me, I don't know about you, but I like writing these little functions. It feels like I don't need a DSL embedded in string literals in my source code, which is my annoyance with just about every possible thing. It's like I'm writing another language inside this one language. Why am I doing that? It feels wrong. This feels like I'm using Go all the way. And read transactions look really similar, but instead of update, we say view. And the trick to know about this is that all of the things you get out of Bolt are only valid within the transaction. If you return from that function there, if you still hold a copy of the value you got from bucket.get, things will go wrong. The data will not be the same as when you last looked at it. So, lifetime of everything you receive from Bolt is in the scope of the transaction. And that's one of those things that, I made that mistake. I discovered it like 2 weeks ago that I had made that mistake, and it was in my code base for 6 months, I think. So it's an easy mistake to make. But this is unavoidable, and anything that would do, like, if you guys, have you used sync pool, for example? It's a way of instead of churning through garbage, creating garbage for the garbage collector, it has a pool of objects that are managed a little bit more explicitly. It has the exact same thing. If you return an object into the pool, it's essentially the same as the old C use after free bar. It's kind of the same thing, except the language makes it a little bit safer. But it's still that's one of the typical bugs you can make. So you that's the one sort of trap, I'd say, that you kind of want to avoid. So we talked about having a single write. So what about the read side of the picture? So we can have at most one write transaction, at most one update call at a time happening. If another one tries, it will wait until the first one completes. Of course, that makes no sense for reads. You want to have as many reads going on at the same time as possible. That's where the performance comes from. Even in SQL databases, you have this thing called isolation levels, which is like how the database vendor describes the behavior of the database for your queries. Snapshot isolation is pretty much, I think, the strongest possible thing you could say about a SQL database. So Bolt is that level. So once again, it's really the most easy to reason about. So what happens is when you start a transaction, you call db.view, or let's not go into that yet. When you you call db.view, you have a snapshot of the database as it was at the time your transaction started. And throughout this whole function, you will be reading that same snapshot. So if you read the same value again, it will still have the same old value. So here's an example of that. We have a writer that will, every 100 milliseconds, write the current time of day into a single key called clock. And we delay a little, and then start a transaction that also delays a little, and then we say we are observing the clock as of this time. So what happens when I run this is that you get a bunch of updates. Scroll. There we go. So you have a bunch of updates going 0, 1, 2, 3, 4. You have regular updates to the clock. And the transaction started here, but it only read the value here, and it's still seeing the old value. So it's perceiving a snapshot of the database, which makes it easy to reason about. Things don't mutate from underneath. And when you start the transaction, you have a consistent world. And one of the things that makes Bolt nicer than many other key value stores is that you can use nested buckets to kind of structure your data. So instead of needing to cram everything into a single namespace, where you need to encode into the key that this is my customer ID this, and this is their whatever. You can, for example, put each customer into a separate bucket, and underneath that customer, for example, every, I don't know what's the right word, product is a new bucket, and under that is something. So you can structure the data with buckets that are essentially like folders where keys and values are like files and contents. Does that make sense? So buckets are created with a called create bucket. And you just get a reference to a bucket object, and you can call methods on that to dig in deeper, whatever makes sense for your application. And once again, these things, the scope of the bucket value is the transaction. So you can't hold on to it. And when you use them, you just ask to get the bucket by this name, and it's either a nil or you get the actual bucket. And if you call a bucket, the .bucket method on a previous bucket, it's a sub-bucket and so on. And there's essentially no limit on how deep you can dig with this. There's a little bit of overhead, so you don't necessarily want to create a bucket per, an object, a struct, where every field is a key. That's a little bit much. So it's once again, Bolt is not a document store, like the way, Elasticsearch or Mono or whatever it is. That's not quite the level it's meant to be. So what you have is you have the database that has transactions pointing to it, and one of those transactions is the special write transaction. There can be only one write transaction at a time. And inside those transactions, you have cursors that are either iterating the top level, or you have buckets, and buckets can point to other buckets, and a cursor can be walking through a bucket. But this is essentially just a hierarchical tree accessing API, where you just walk down a tree, and you can walk through a node and ask what keys are here. One of the really neat things about Bolt is the way it's implemented. And this is largely the LMDB inspiration here. So what they've done is that the whole database file is memory mapped as a read-only area of memory. That file literally is in memory. As far as everything is concerned, accessing that range of memory reads from the file without needing to do like syscalls, without needing to explicitly ask for file.read, whatever. None of that sort of stuff. The file is in memory. And the read-onlyness makes it safe, so you can't accidentally write over it. So what Bolt does is when you do edits, when you commit a write transaction, when you call update, it writes to the file, but all of the reading goes through the mmap. So if your machine has enough memory, it behaves as if it was an in-memory B+ tree. Which is kind of awesome when you think about it, because usually, like, in-memory data structures are fast, and on-disk data structures are slow. But now, if the active working set of your tree is small enough to fit into memory, it literally is an in-memory data structure. And there is also no like double caching, where the database library needs to maintain a row cache or something, and go through like, this is within the 1,000 most requested rows, let me hold it in my cache. All of that is done by the kernel. And the big benefit of that is that, first of all, the kernel, you can sort of assume that kernels are really well written by smart people. And second of all, the kernel has a global view. So it doesn't matter what gets thrown out of memory. It could be part of your database. It could be that JPEG that you haven't served anyone for a while. File caches. It could be part of your executable that is only used once a month. Everything unnecessary gets thrown out of memory to make room for your database. Or if something else is more required, your database gets thrown out of memory because it wasn't the active needed thing. So it's this weird thing where writing simple things creates something beautiful that performs well. And I really like that. That's like just when everything just clicks together. So this is why you can't hold on to the get return values, for example, because those byte slices are literally pointing to this region of memory. And now remember, it was a copy on write B tree with space being freed up and reused. So there's no guarantee when this bit of memory will be reused once you've ended the transaction. The transaction holds it pinned to the old usage. But when the transaction ends, that memory can be replaced with something else, some other content. That to me, I knew of LMDB before Bolt existed, and I was trying to use LMDB through the Seagull bindings, and was kind of into it. I liked the idea. And when I realized that Ben is writing Bolt to kind of imitate this model, I was like, yep, that's a solid winner. I like that. It makes read operations really easy and lightweight. I think a read operation right now is something like 40 nanoseconds, which is kind of hard to beat with anything that would normally try to do things the old way. So here's what happens if you try to accidentally change the values returned to you. It crashes hard. So you get a paging failure. This page was read-only and you try to write to it. So if you ever see this, you kind of know what you did. You probably failed to allocate a new buffer and copy this value into it. So the downside of being memory mapped is that the Bolt database pages are exactly what the kernel thinks they are. I didn't say what's stored on disk. That is fungible. But the Bolt database pages are what the kernel thinks they are. So there's no load operation during which we could do decompression. Like LevelDB, for example, when it writes a chunk of content to the disk, it compresses it with snapping. And when it loads it from disk, it decompresses it with snapping. Now, with Bolt, there is no such thing as loading. It's just memory accesses. So there is no convenient moment to decompress anything. And I kind of think that that's kind of unnecessary because these days a lot of stuff can compress files for you. So, for example, with ButterFS, you can tell this file should be stored compressed. And there's actually pretty good benchmarks. If you say all of my files on this disk should all be compressed, your system becomes faster. Which is kind of an interesting little point. Why is not? That should probably be the default soon, huh? There's also plus capital C, which says, hey, ButterFS or any other copy and write file system, don't give me the copy and write protection that you normally give files, because this is an update in place file. So, avoid that overhead because it is pointless, wasteful. And it's the same thing that you would do to, for example, a virtual machine disk image that gets, individual blocks written to. It's not like a single file that gets rewritten from scratch. So you can kind of optimize how things are done. If you're not using one of the fancier ones, one of the fancier file systems that has this stuff, you can also put the whole the whole block device on something that compresses things on the fly. So DM compress is a block level compression solution. But that kind of is the downside, is that you don't have the flexibility of having custom code that loads things from disk, because the loading is done by the code. Okay, Bolt is decidedly low level, in case it hasn't kind of come through yet, is like, this is not really Bolt's problem, this is the application's problem. A lot of these things actually kind of even belong in the application, because then you can do things in a way that is smart and takes advantage of what you know in the application. So Bolt doesn't do things like schemas, indices, queries. There is no DSL. There is no like filtering of, give me all the keys that have the value hello. There is no such thing. You either walk through all of them, or you write an index that helps you do that thing. And what I kind of want to see is a little ecosystem of indexing built on top of things. So for example, there is no reason why, there's that project BLEBE, I think, I'm not quite sure how you're supposed to pronounce that. BLEBE, that's essentially a search engine, the guts of a search engine, written in Go. There is no reason why you couldn't take one of those things that is a fairly generic engine and store the index in Bolt or whatever, and update it from your application. But that's kind of outside of the problem domain of Bolt itself, and that's actually really relieving, because you know that Bolt is pretty much going to be what it is. Like, it's not something that is going to live for the next 2 years and be something else. I actually kind of like that it is fairly stable now. We're still talking about some additions, some minor API changes, but we feel like it's pretty much like definitely a 1.0 now. So a good example of what is not Bolt's problem is a sequential transaction batch. So the idea of, in the same disk sync, doing multiple updates in that one synchronization operation. And this is something that a SQL database would do for you. It would combine multiple queries that you send in, multiple, like not queries, but multiple transactions that you send in. It would combine those and do multiple of them at once. And this sort of stuff kind of isn't Bolt's problem, especially when it's sequential. So like, imagine the idea of you wanting to import a file that has 10 million lines, and you create a key for each line. Now, the trivial way of doing it is read a line, parse it, update, set one key. Read the next line, parse it, update, set the key. The problem with that is that you're doing 2 full disk syncs for every line. That's 20 million disk syncs, which is going to take probably hours. That's not good. So what you do instead is you want to batch multiple updates into one. So let's say you parse 1,000 lines, do a transaction that writes those out. And you can make that be streaming, so you're not holding them in memory or anything like that on your application level. And the reason why that belongs in the application is you don't know whether it worked until the end of those 1,000 lines. So you can't have the same simple API where you say, put this, tell me if it worked, if you're trying to sequentially batch them. Instead, you need to actually do this batch and then check whether it worked. We are doing a thing we call db.batch, which is taking concurrent operations and merging those into a single transaction. So for example, if you have a web app, an API of some sort that takes incoming requests and does something to the database as a result of those requests, with this thing, let's say anything coming in within the same 10 milliseconds up to a limit of 1,000 operations gets put in one transaction. So we have that, but it is for concurrent transactions, not like let's import this one file kind of operation. So Bolt is a key value store. So no relational databases, no SQL, no queries, nothing like that. Simple. It is written in pure Go. It's a pretty project. It is a simple project, and it is surprisingly a really small project. It's a library, it's not a service, it's not a daemon you run, it's something that becomes part of your application. It's meant to be, the Bolt database is meant to be used from a single process. So you really own the file that you have opened, nobody is using it at the same time. So for example, SQLite will let two processes open the same file, and it pays the overhead of doing that. Bolt kind of tries to go for the simple thing, and it doesn't pay that overhead. The key value store is ordered, and you can use that to do interesting things like, for example, I store directory listings in Bolt, and I know that I can walk them in alphabetical order, just because it's an ordered key value store. It is internally a B+ tree, which kind of works. It's like one of still kind of the state-of-the-art data structures. I mean, you can do better, but not much better. So B+ trees are pretty neat. It is based on the idea of there being at most a single writer at a time to the database, and that makes application logic really simple to write. On the reading side, you get snapshot isolation, which means whenever you're reading from the database, you have a consistent worldview. You don't have to deal with things changing from underneath you, and you can use nested buckets to structure your application. Bolt is internally built using mmap, which is a really neat trick and works really well for Bolt. And it kind of is a low-level tool. So it may not do what you want, like directly out of the box, but it is really like workable when you think of it as a library. You need to kind of embrace the fact that it is just one of the things that your application uses. And I really enjoy using it, and it has been a great match for my application. And I would like to hear, like, you maybe later, once all the talks are done, come to me and talk about, like, I have this and this thing. Could your Bolt be useful for this and this? That sort of conversations are, in my mind, really useful because you get to kind of evaluate, does this fit this mental model at all? Would my application benefit from it at all? But that was the talk. Any questions? Yeah, in the back.
Is there a mechanism to do a backup and a restore?
Good question. Yes, of course there is. So if you read the file, the database file, from outside the process, it can change from underneath you. So that's not a safe way to do a backup. So what Bolt actually has in the library is you can call a function, and it will essentially write a copy of the database that is a snapshot to your thingy. I forget whether it is, I think you hand in an IO writer, and it just writes a copy of the database to that IO writer. Okay. Also, if you have any solution at all that can give you atomic snapshots, which, for example, ButterFS does, that's a perfectly valid way of taking a backup because Bolt is crash safe. So even if you kind of catch it in the middle of doing changes, it will roll back to the previous thing. Okay, yeah, behind?
Under what circumstances do you reestablish a memory map?
Re-establish the mmap.
For example, the underlying file grows. How do you get...
Sorry, the underlying...
If the underlying file grows, how do you get memory map access to it?
Yes, so mmap is a fixed range of memory. You can't, like, change the size of it without mmapping something else. So when the database runs out of free pages and needs another free page, what it does is it increments the size of the file and re-mmaps it with the bigger size. And now it has a bunch of free pages. Does that make sense?
Yeah. I might talk to you about afterwards if there's any question about if the pointers change at all. Do you have any
well, basically, you're not holding on to any of the pointers. That was the whole point of, like, the values that get returned to you are only valid within the transaction.
What about the performance? Since it's a single writer, can it become a bottleneck in my application? Did you do any benchmarks?
So, the thing with the single writer, if you remember what I said about the copy on write B tree, where are we? There we go. So, to flush out a commit, Bolt needs to write all of the dirty pages, make sure they are stable on disk, then write out a new metadata page and make sure that is stable on the disk. and then it says we're done. So every transaction, every update call costs 2 disk syncs. And that kind of is your answer. Honestly, how much data you write is almost irrelevant because the syncs themselves are the cost. Now, an SSD will do like some hundreds of syncs per second. So that's your limit. And that's where the motivation for the batching mechanism comes in. The read side, when things go well, it's literally an in-memory B+ tree. And I am getting timings of 40 nanoseconds, which in my mind is pretty darn good. So Bolt is definitely meant to be a read-heavy solution. And the way I think of it is, if you're building something that is not, let me take that. So Bolt is not a network service in itself. So there is no such thing as multiple things coming to Bolt directly. So there is always your application mediating that conversation from any clients you have. So in that sort of a situation, your application is the perfect place to do some sort of batching. And it puts you in charge of the error handling, what if the batch fails, you know, that sort of stuff. And DB batch, for your average network application that does something in the style of RPCs coming in or requests coming in, DB batch is pretty much what you need. It's close enough to the perfect solution that, in my mind, is completely an acceptable solution.
One more question, quick one.
Thank you.